Let's look at the relationship between polynomials, but now that we're using complex numbers. One of the interesting things that occurs is this: if all the coefficients in that polynomial are real, then when we factorise it, those roots must appear in conjugate pairs. What that means is every polynomial of degree n, we know it can be factorised down to a mixture of quadratic and linear functions. That's over the real numbers. We're just using real numbers. But once we go into complex numbers, that now means everything can become a linear factor. Right? Some of them might involve complex numbers, but we can create n linear factors. What that also must mean is if your polynomial is of odd order, a cubic, a pentic and so on, there must be a real solution. Because if the complex ones or the imaginary ones are appearing in pairs, well, that will only give you an even number. So there's always going to be one left over at least. Okay, so very simple one then. X squared plus 2x plus 2, which before we said, oh no, we can't factorise that. But of course now we can, because we can rewrite that as x plus 1 squared plus 1, which is really minus I squared, difference of two squares, x plus 1 plus I, x plus 1 minus I. So we can factorise it down to linear factors. Z to the power of 4 plus z squared minus 12 equals 0. We want to solve this equation. Well, it's one that looks like a quadratic, so I can still use the idea multiplies together, adds together. I come up with two factors. Now, if I wanted to keep factorising down to linear factors, I could. It's an equation. I suppose I don't really need to, because I could solve it at that point. But for the sake of the factorisation, we'll keep going. The first one, not a problem with real numbers. I can make that z plus root 3, z minus root 3. That would be factorised over the real numbers. The z squared plus 4, I would have to use complex numbers to factorise it down to linear factors. That would be the factorisation over complex numbers. And there's our solutions. The reality is, as it's an equation, I didn't really need those factors. I could have gone straight from the second line and said, oh well, the first factor has solutions plus or minus root 3, the second one plus or minus 2i. Now remember our factor theorem then. When we're looking for factors, we know that if x minus a is a factor, then when I substitute a in, I should get 0. And if it's ax minus b, then it would be b on a would be the factor that we're looking for. Let's factorise this cubic. It's a cubic, so I know there must be a real factor. Let's try and find it. We know the constant is 5, which nicely is a prime number. That only gives us a couple of possibilities. But the coefficient of x cubed is 2, so maybe there is a fractional factor there as well. The logical first one to pick, of course, is, that's right, negative a half. And when we try negative half, oh look, it becomes 0, that works. Okay, so we now know that 2x plus 1 is a factor. And then we could do a polynomial division, or just looking at the terms to come up with the other factor. X squared minus 2x plus 5, which then I could go and factorise that one. It's a quadratic, so I can write it as difference of two squares. And there we have it, 2x plus 1, x minus 1 minus 2i, x minus 1 plus 2i. Alright, this time we've got a quartic and we're told it has two rational zeros. Well, if they're rational, they're real. Find these zeros and factorise over the complex field. Well, let's find the two rational ones first. This time the constant is negative 3, again 3, prime number, lovely, so 1 and 3. But we got this coefficient of x to the power of 4, which is 4, and 4 has got factors of 4 and 2. That brings up other possibilities. So again, we go for the logical choice first, which is a half. Oh, that turns out to be 0. Fantastic, I've got one of the factors. Now I know 2x plus 1 is a factor, which means it does factorise to be 2x minus 1 times something. Leading terms times leading term must give me leading term. So I know 2x cubed, and then in the other one, constant times constant is a constant, plus 3. Create the other terms. Okay, we've got our second factor. We do know, though, there must be a rational one in the second one as well, because they told me it has two rational ones. Logical one to pick. Yeah, negative 3 on 2. That seems logical. Oh, look, that works. We get 0. So the other factor is 2x plus 3. We now know the two rational zeros. They're a half and minus 3 on 2. It does want us to complete the factorisation, so let's keep going. So leading term times leading term. I know I've got x squared, and then I need to get negative 3 as the constant, so that must be plus 1. The question now is, how many x's do I have? Well, okay, well I know that 1 times 3 times 2x would be 6x, and 1 times 2x times minus 1 is minus 2x. So at this stage I've got 4x, I want 1x, therefore I need another negative 3x, giving me the missing term being x. And then I could go and factorise that. Now, notice my factorisation here, I leave them as fractional in the factorisation, because it's not an equation. If it's an equation, not a problem. I could write that first factor as 2x plus 1 plus root 3 and so on. But it's not an equation. If I was to write this factor as 2x plus 1 plus root 3i, and the other one as 2x plus 1 minus root 3i, the expansion of that would not give me 4x to the power of 4, because it would go 2x times 2x times 2x times 2x. That wouldn't be correct. So because it's a factorisation, I need to leave it with these fractions in there rather than making them whole numbers. If it's an equation, not an issue, because if it equals 0, and it doesn't matter if I have a multiple of it. We have another quartic. This time we're told it has a real root of multiplicity 2. In other words, there's a double root in there somewhere. Well, this time I've got a lot more to investigate, because it goes into 45. Factors of 45, 1, 3, 5, 9, 15 and 45. At least it's monic, so I don't have to worry about fractional ones on that. They told me other information. It's of multiplicity 2, so I also know that it has to satisfy the derivative as well. And maybe that will narrow it down a bit, because it's got to go into now negative 30. So I know the number's not 45, and it's not 9. All the other ones are possible though, aren't they? At least it gets rid of some of them. Logical first one to pick. Actually, it is 1. I tried this time, but it didn't work. So we know 1's not the double root. Then I tried 3. Well, 3 worked for the derivative, but remember it's got to satisfy both of them. Does it work for the other one as well? And it does. Alright, 3 is the double root on this one. We now know x minus 3 squared is a factor. Okay, what is the other factor? Leading term times leading term. At this stage I've got z squared. I want z to the 4, so it must be z squared. Constant times constant. This stage I've got minus 3 squared, which is 9. 9 times 5 is 45. Okay, what shall we investigate? The z's? Alright, let's investigate the z's. This first factor would give me minus 6z. Minus 6z times 5 is minus 30z. Looks like I don't need to go any further, because that's what we want. We want minus 30z. So that must be our factorisation. But it did say to solve it. Let's go and solve that. Did I need the second last line? Again, it's saying solve it, so I probably didn't need to reduce it down to its linear factors. But the solutions are 3 or plus or minus root 5i. Here's a nice little question from a few years ago now. We've been given 3 complex numbers, and all we're told about them is their moduli are equal, they add together to give 1, and they also multiply together to give 1. We've got to find those complex numbers. Here's how I did it. From the last line, I know the modulus of z1, z2, z3 must equal 1. But I also know the individual moduli are equal. That's now telling me the moduli of z cubed must equal 1. So the modulus of z3 is equal to 1. And in fact, I could do that for each of them, because they're all equal. So modulus of z2 is equal to 1 as well, and modulus of z1 is equal to 1. Okay, tells me something. Also playing with the last one. z1 times z2 must be 1 on z3. But we said the easy way of finding the reciprocal is the conjugate over the modulus squared. But we just discovered the modulus was equal to 1. So in fact, z1 times z2 is the conjugate of z3. And I could have done the same with the other ones. So z1 times z3 would be the conjugate of z2 and so on. So what that now means is all of those pairings added together would be the the same as adding the conjugates together. But the sum of Z1 plus Z2 plus Z3 we're told is 1. So this is also equal to 1 because the conjugate of 1 is 1. So why does that help me? Or how does that help me? So what I now know is Z1, Z2 and Z3 must be the solutions to this equation. So I'm saying minus sum of the roots 1 at a time, plus sum of the roots 2 at a time, minus sum of the roots 3 at a time, or product of the roots. But we have found a value for each of those three things. So Z1, Z2 and Z3 must be the solutions to this equation. Okay, well let's just go solve that equation. It factorises nicely. There are the solutions. We've now found Z1, Z2 and Z3. I suppose which one you make Z1, which one you make Z2, which one you make Z3 doesn't really matter. Basically they're the three answers that they're looking for. All right. That shall do us for today.